From NREL.
Thank you. Over here you see yesterday evening sunset on the river here, going back to the thing Sean and Gary were with me. So hit it just right. It can look like that, but instead of just a rainy thing that we had all day today, I haven't seen much weather is outside right now. But I'm going to talk a little bit about light management and organic PV type thing, and a little bit about plasmons and other approaches to do that. So this is an overview here. I'm going to give a short introduction here to light management. Is it on? Or is that much higher? Is this better, or do I? Okay, I'll button up. I'm sorry. All right. Everybody hear me? Excellent. So I'll talk about light management in organic solar cells, and this is a fairly classical thing, just to give you a short introduction, because this is supposed to be a little bit of a tutorial session, so I threw in a little tutorial in the beginning. And then I'll talk more about some actual recent science that we've been doing on plasmonic absorption enhancement. And then lastly, where my heart lies here, using plasmon polaritron hybrid states with the excitons. And I'll explain all this, so you don't need to really know much about this yet. Okay, there we go. So light management and organic PV. And as we've seen this morning in Sean's talk, these organic PV solar cells are very thin layer systems. And here's a typical sort of overview, glass slide, ITO, P-dot. There's an active layer there on top, and this can be a bilayer, or this can be multiple layers there. And that's typically in the order of hundreds to several hundred nanometers thick. And then there's a top electrode, typically a metal like aluminum. Now, you can think about this, of course, if you have light coming in there, that light is going to bounce around multiple times, it's going to interfere with itself. And so it's really important if you start thinking about, well, how much light can I absorb in my solar cell? You really have to think about these effects. There's optical interference effects in these things. Now, there's a wonderful model out there. It's called the optical transfer matrix method. And what you really do there is just keep track of every interface in your device and think about what is the reflectance there, what is the sort of optical interaction in the layer, and then you can write this all out, and you can get to what is the light intensity strength. So here that's the electrical field component of the light squared as a function of the position in the device. And here's a nice example, and in Pentacene they wrote this paper that really gives a very good overview of doing this, and they simulate this bilayer device of this 5 bit and with a layer of C60 on top. And if you just play with the thickness of the C60, you can see that you can shift the maximum of the light intensity from basically the donor layer here into the acceptor layer. Now this obviously has enormous consequences for what the final photocurrent of the devices can be. So you really have to think about these effects and really take that into account if you want to know the real light absorbance and how much current you can get out of your device. So there's tricks there that you can play. Like I say, you can change the layer thicknesses and all these sort of things. But here's a nice example of where people use the little zinc oxide layer. And the zinc oxide layer has the effect of what they call an optical spacer. And that shifts, as you can see, the intensity maximum of the light here, the electric field, shifts it straight into the PVHD layer, while before it was in the P-dot layer. Obviously a pretty bad situation. And you shift it into the PVHD layer, and that increases the current by quite a bit. And here are some varying experiments, basically, with and without the zinc oxide. And with the zinc oxide, you have a higher maximum photocurrent coming out of it in the measurements and in the theory. Now Here, another example, and here, this is really important actually, if you make a tandem solar cell, so you have two of these organic PV cells stacked. To make that cell work, their current has to exactly match, and you can try and optimize this. And here's an example here from Parnell actually, where you calculate the current from the bottom cell and the current from the top cell, and as a function of their thickness. And these two curves have an intersection, and that intersection is where you want to be, because then the number of photons absorbed in each subcell is exactly equal. And this is not trivial, as you can see. This is a very convoluted pathway where you can either choose like 150 here and only 100 there, or basically similar further. In this thing, you can also see there's a problem here, of course, that what is assumed is basically that each photon that you absorb in each cell actually leads to current. Now, in a real device, that is not true, because if you make a really thick device, you can imagine, you make a device with several microns thick, then no charge carrier is actually going to arrive, because there is so much recombination at that point that doesn't work. So what you really want to do is actually simulate to the charge transfer. I'll talk about it in a little bit. Here's another example. This is not an organic solar cell, but a quantum dot solar cell. These are also excitonic systems, where this looks almost exactly like our organic PV system. Actually, at ITO, there's these lead selenide dots sandwiched, and there's between the ITO and this top electrodes, which is calcium aluminum again, exactly like in the OPV system. These layers are a little rough, as you see here, so here they actually take the roughness into account too and do the optical modeling. And these are reflection measurements of the entire cell, and you see the model follows almost exactly the actual reflection measurement, so that's really nice. And then from the model you can calculate, well, how much light is actually getting absorbed in that lead selenide nanocrystal layer. And from that, and the current that you measure, you can get to what's called the internal quantum efficiency. And this tells you exactly how many carriers do I detect in the external circuit per photon absorbed. And that's a very important quantity that they needed to know in this study. And so that really allows you to, as you can see, if you go thicker and thicker, so they start at 60 nanometers, the internal quantum efficiency is quite high, 0.8 here. And when they go to a very thick cell, you see there's almost nothing left there. It's 0.2, 0.3 of internal quantum efficiency. A similar thing happens in the organic solar cell, by the way. So what you really need to do is both model the optical fields and then solve all these equations. And Sean talked a little bit about that. I won't talk really much about it, but then if you have the actual generation rate as a function of the position in the cell, then you can sort of start thinking about, well, what actually happens to the carriers that you generate. Do they recombine? Are they actually collected? And then get to a full model of the solar cell, basically. And in principle, then you can get from those mobilities and all these optical constants, you need to optimize these things and find a maximum efficiency condition that takes into account both the recombination and the optical absorbance in the cell. We're going to release this pretty soon, as soon as the lawyers actually allow us to do that. That is the biggest impediment at this point. And Peter is coding all this, and he has done the electrical model and is putting the optical model right in front of it, so people can just download it and play with these things, and I think that would be very useful. And here's some other examples where people have done similar things in the literature. So now I want to change a little gear. So I've talked a little bit about knowing the importance of knowing how much light you actually absorb in your cell, and to balance the amount of light absorbed against the fate of the carrier, so the recombination. And for that, so I'll show you that surface plasmons are a nice little trick that you can play to get more light absorbed. But first I need to explain a little bit about what these things actually are. So a little bit of background is probably good. So what are these things? I see that I put another slide in front of this that I didn't think about that I actually had here, but this is a similar slide as to what Sean showed in the OPV part. You can see this exponential growth of surface plasmon research. You see it's about 2,500, so almost exactly the same as what you said for OPV, so it's basically the same number. And if you combine that with solar and photovoltaic, you can see there is something like 40 publications a year where people combine solar and surface plasmons. So it's a very rapidly growing field, as you can see. What are they? So how I explain these things, basically, that you can think of them as electromagnetic waves, so light, basically, trapped at the surface of a metal with a dielectric. And this happens through the interaction with conduction band electrons or conduction electrons in the metal. And this is schematically shown here, where you see these field lines on the surface of this metal, where you have these charge oscillations, these pluses here, minuses here, pluses here, and that gives you these little field lines. And you can think of this as a photon basically trapped at the interface. Now normally these things in a flat interface are not normally generated by themselves. That's because if you look at this, what's called the dispersion relation, this is the line for free photons, so it's just in space, so it's a linear relation, a Boyne relation. And surface plasmons have this curved relationship, and you can see that a photon normally doesn't have enough momentum to generate a surface plasma. So what you need is an extra little jolt, this G here, to generate surface plasmons. Now there's several ways to do that. One way is to use a nanostructure, and there's an old example actually. This is a little metal nanoparticle. This metal nanoparticle can slosh its conduction electrons up and down in response to the electric field of the incoming light here. So, and as you can see, that there forms a little oscillating dipole that can actually absorb light. And that effect has been used for hundreds and hundreds of years, and this is the oldest example known. This is the Lycurgus chalice, as it's called, from the 4th century. It's a Roman cup, and this uses these 17 nanometer gold nanoparticles inside there. And this is quite spectacular because if you, instead of in transmission, look at it in reflection, it looks bright green, and in transmission it's this beautiful blood red. Other examples people have seen, of course, the stained glass windows. Those are also gold nanoparticles inside the glass there. Now, when you do this, you have these conduction electrons sloshing up and down. You can see that this charges right at the surface there. Cause very strong electrical fields right at the surfaces of these particles. And these can lead to all kinds of effects, and this is an actual application that it's used for. You can enhance Raman signals from molecules absorbed to the surface. And the record now is in the order of 10 to the 40 times better signal from it, so you can actually do single molecule Raman using this trick here. This enhances fluorescence, absorption, and light scattering, and all these sort of things. So it's quite neat and perhaps useful. So here's an example of calculating the electrical field around gold nanoparticles. These are little spherical particles. And you can see that you get local enhancement of about, in this case, it's 50 or higher near the surface of the optical electrical field. Here's another example where these enhancement is actually much larger, a little prism type silver particle, and you get hundreds of times of enhancement of the electrical field at the apex of those prisms. Another example, and this starts going more into the relevant area for organic photovoltaics. Here we have a dye that is separated by a certain distance from a gold nanoparticle, and we look at the emission rate from that dye. So this is basically just the fluorescence intensity, and you can see that there is a factor of 6 or more enhancement in the fluorescence intensity of that dye And then if you move the particle away, this is done by a spacer that's sitting in between there, the rate goes down. And that follows this relationship that they calculated very nicely. Also, you see that if you get very close to the metal particle, then another effect occurs in which you have actually loss of the fluorescence intensity, and that's because of energy transfer to the particle, and you actually lose energy. So that's something to be mindful of. Here's another example. This is polyfluorine on silver particles that are sandwiched between P dot and ITO. So here we actually have a spacer layer. This P dot PSS is a spacer layer between the silver particles and the polyfluorine. And you can see this, the presence of the silver increases the PL intensity of that thing by a factor of 3 or so in this case. And the same happens for NEHPPV. Now this bodes quite well because these are nice, of course, organic PV materials that perhaps you can enhance the absorbance of these materials this way. So, enhancing absorption using surface plasmons. So, go back to what the problem is in this case. If you make your solar cell very thin, now you can collect every carrier that you create because the transport is so much faster than the recombination in this case, so that will be really good, but you cannot absorb a lot of light in that case, and that's problematic. Now if you make it much thicker, then you can absorb all the light that's coming in, but you cannot collect them, so that doesn't help you either. So what you need to find the optimum here. The optimum is maybe not always the best optimum that you can find. Now, if we can somehow increase the amount of light absorbed in this layer, that would be great. And one of the solutions for that could be those surface plasmons. And since we know they increase the optical electrical field near their surface, that might indeed work. And we know that the absorption processes scale with the square of the electric field of the incoming light. This might actually work. And it might allow you to use very thin layers that still have good absorption, so you actually can collect more of the carriers, you can have higher open circuit voltages, all these sort of things. So you can have it all basically. So an early example of using surface plasmons in organic photovoltaic type systems. So this is the oldest that I know of. This is 93. Here they use a copper phthalocyanine little cell that's between silver and aluminum. It's just a layer of copper phthalocyanine basically. This is a little experiment in which you can either you can select whether you want to excite the surface plasma on the silver or not. And it turns out that when you excite the surface plasma, you get this peak in the photocurrent, and there's a big enhancement over there. And when you don't excite, you see almost nothing. So, this certainly appears to be possible. Now this brings us to thinking about, well, how would you go about adding these silver nanostructures or whatever to the cell? And there's these 3 common strategies that you'll find in the literature. One of them is you take silver particles or metal particles, it doesn't really matter. You put them on the front of the cell where the light comes in, and now you get a forward scattering effect, so the light actually scatters on that surface plasmon and goes into the active layer, and then you get an internal reflection effect in which it keeps bouncing around. So that's that forward scattering. The other one is to put the particles right inside the layer, and you get the direct enhancement of the fields around it. And the first is to use these sort of gratings, and these gratings have a nice effect if the light coming in, and they refract the light into this sort of waveguide mode that sits there. I won't talk about that, but that is a nice strategy that people are actually pursuing. This comes from an excellent review article that recently was published. If you're interested in that, I urge you to check this one out. This really gives a very nice overview of this, doing this. I mostly talk about these first 2 strategies actually. So examples in OPV that I'll talk about, using silver pancakes, what I call them in organic solar cells, nanohole arrays, and colloidal particles. First, I'll talk about nanoparticle layers. There's a very simple way to make these things. You take just a piece of glass with ITO, you vapor deposit a little silver, and this spontaneously breaks up into these little pancakes that lie on top of the ITO. This is a well-known substrate for surface-enhanced Raman spectroscopy, if you just do it as in glass, not an ITO, of course. I just showed you some examples where you see the strongly increased PL of these conjugated polymers. This is what these things look like. So this rough structure that you see beneath there, that's the ITO, and these little dots, those are little silver pancakes that are lying on top of there. This is their particle size distribution, typically, if you look at it. So it's about 10 nanometers particles. And here you can see their optical absorbance. So these are surface plasmon active. This is the surface plasmon absorbing here at around 450 nanometers. And the more silver you put on, the more particles you generate, and you just get a deeper absorbance there. Now, on top of that layer, we build a little organic solar cell. And indeed, if you don't have that silver over there, you get a certain current and a certain efficiency. A little silver, and we can almost double the efficiency up. More and more silver, and it goes down again. You can see the efficiency rapidly decreases again. Now there is a little trick in here that we actually used a very thin organic solar cell to start with. And so the effect is much more dramatic than when you would have an actual optimized solar cell. But it clearly illustrates this. And there's now some other examples in the literature where people use these sort of things, and it works really well. And there's actually a group of David Ginger that have actually done this with silver nanoprisms, just like I showed you in those calculations before. They get very large enhancements, and that works really well. So why does this current increase? Now these are the internal quantum, the photocurrent per photon impingement on the cell as a function of wavelength. And you can see that this is the reference sort of cell device here, the continuous line. You add just a little bit of silver in 1 nanometer, this jumps up over here on the red, and you don't lose an awful lot over there. But if you increase the amount of silver, you start losing a lot of current over here. And this is replot the same data, just basically divide the quantum efficiency of the device with silver divided by the device without silver. You can see this big peak here of where you get a lot of increase, but with very thick layers you lose quite a bit over there where the silver itself absorbs. And so, of course, at some point, if you deposit a lot of silver, it starts just being a mirror, and no light actually goes into your cell anymore. And that doesn't work. We can show that it's really increased absorbance. This is a little experiment where we take just the active layer, and there's no top electrodes on there, so there's no alumina on there. You just measure the transmittance and the reflectance of the device. You measure how much light is actually absorbed. As a function of the thickness of this spacer, which is that p-dot layer. If you don't use a p-dot layer, you get a really large enhancement here in the red part of the spectrum. And then if you increase the thickness of the spacer, that enhancement decreases very rapidly. And you see at 100 nanometers of spacer, there's basically nothing left there. And that follows a more or less exponential relationship with the thickness, which is exactly what you expect for a near-field enhancement effect on the surface plasma. You can simulate this behavior, and this is an example of finite difference time domain simulations. So this is basically just solving the Maxwell's equations around this little structure. So this is a little gold pancake in this case on top of glass with an organic on top. And we have a light coming in, and this light excites this particle, and you can see the particle actually beating afterwards. And so the light pulse is long gone by, but it's still emitting intensity. And if you actually take that time-dependent simulation that you saw there, and you just average this over time, you get the actual field enhancement around this pancake. And then we take a cross section above the pancake, and you can see that's basically that same exponential dependence of the field enhancement as we saw in the experimental data. So that's pretty good evidence that that's what's happening. That's what's happening. Of course, what you really want to do is put silver or gold particles inside the active layer. This is an example of some silver particles that we made. This is not that hard to do. It's very simple to make very nice monodispersed particles. What you get, of course, is that you have closer proximity with the absorbing layer, as we just saw. If you get that to 0, then you get a really large enhancement of the optical absorbance. But there's large problems there that if you have these metals sitting inside your active layer, they will start acting like recombination centers, very obviously, and you'll start actually losing a lot of current, probably. And that's why no one has actually conclusively shown that this really works. People have used these as interconnects, where you actually use the fact that they act as recombination centers very well, because that's exactly what you want to happen over there. So there's an interconnect between two organic solar cells on top of each other. You want areas to recombine there, so that works. But if you put that in an active layer, this might not really work. On the other hand, you can chemically tailor the surface of these particles and make them compatible with the organics, maybe. So that would be pretty good. Now we've done a little bit on this. Here's an example of 2 layers in which I just use PVHD PCBN reference film. That's the green here. The other measurement here is with a little silver nanoparticle in there, and these silver nanoparticles absorb, as I showed you before, around 450. That's what this little peak comes from here. But you can see that the enhancement of the absorbance extends all the way out to 800. This is just the enhancement of the absorbance there. However, if you make a solar cell out of this, then all these things happen that I talked to you about before. This is a reference device here. It's the same thickness, but if you add the silver nanoparticles inside there, you can see really bad fill factors, and you actually start losing voltage from there. But you do get quite a bit more current out of it. So this might work if only we could figure out how to really protect the surface of these particles, that we don't get a lot of excessive recombination. Another example, these are random nanohole arrays in silver. We make these using colloidal lithography. This is basically just using little latex particles that you put on a piece of glass and then evaporate silver over it, and then you rip out the latex particles with a piece of 3M tape or with just sonicating. It's a very simple method. You can use this to make square inches easily of this stuff. You can play with the density and the size of the holes and all these sort of things. And that's really nice. These things show enhanced transmittance, and this is a surface plasmon effect. I won't go into detail why this happens, but if you look at the transmittance of those layers, and here is a function of wavelength, and you divide them by the area of the holes, you can see that you get like 2.5 times or more even of transmittance than you would expect for the area of the holes. So this is an effect in which the surface plasma on one side actually couples in the light and transmits it through the hole and then re-emits it on the other side. And here's the enhanced transmission as a function of the hole spacing, as you see here, and that goes through a distinct maximum. And this maximum is actually caused by the surface plasmon forming a standing wave between 2 holes. And so this is a fairly classical effect, actually. Here's an example. So here you can see that this is one of those finite difference time domain things, and there's the little holes. And if you look carefully, you can see these standing waves occurring between 2 holes. You see, for example, over here where it goes from red to blue, and that's a little half wave, standing wave in between. Now, how do they stack up? As I say here, so we made these little solar cells. This is the silver nanohole array. There's PDOT on top here, thin layer, and then the organic the bulk heterojunction and the top electrode. So there's no ITO here at all. And what we get is basically the same efficiency as a standard ITO design. So this actually works quite well. If we look at the external quantum efficiency with these things, you can see that it's not that good. It's not as good as ITO. This is in a log scale, by the way, to blow up the effect and really make it appear much larger than it is. But you can see that actually at certain wavelengths, the nanoholes do better than ITO, even though if you look at the transmittance spectrum, it's nowhere near where ITO is. And if you normalize these spectra, you can actually see that the nanoholes get a far better, perform far better here in the range where the bulk heterojunction absorbs than ITO over here, and these are clear sort of evidence for these surface plasmon effects. Now I want to change gear a little bit, and these are actually fairly classical effects that we looked at, just using these surface plasmons to basically focus the light into the active layer of the solar cell. This is a much newer concept in which we actually hybridize quantum mechanically the surface plasmon particles with the excitons in the organic system. And there's a whole new sort of universe of effects that we can exploit here. And okay, next slide. And so, how this actually works? Here are some very nice experiments that was recently published. You can actually take, in this case, it's selenite quantum dots, and this sort of behaves like a molecular system sitting on top of the thing. And those selenite dots have these two excitonic states here, and those are the two horizontal lines. Now, if you at the same time generate a surface plasmon, which has points on this line over here, basically, what happens is that when the surface plasmon has an energy almost the same as the exciton on the quantum dot, the levels split up into two levels, and that happens right here. And you can see you get this anti-crossing behavior, and the same happens at this higher lying excitonic states, where you also get these two states being formed. So what happens is that you have these two energy levels, and they just form bonding and an anti-bonding state, as you might remember from undergraduate physics. And so the same happens over here. You get a mixing of the quantum mechanical state of the surface plasmon with the two excitonic states, and that was really convincingly shown over here. Another example here. This is from my own group, where we do scanning atomic spectroscopy on selenites and zinc sulfide particles here. And we can actually detect this second intermediate state being generated on those dots here, directly from the single particle luminescence from these dots in an STM. I won't talk about this just for time's sake, and this one here, but there's many examples here of where you can actually form that quantum mechanical interference and play with it. A really nice example of this, and this goes into why I'm interested in it. This is from Gary Wiedrecht at Argonne. They use this porphyrin dye over here, and what they're able to do is by tuning the surface plasmon, they can turn on and turn off these different kinetic pathways. And so what happens is that just by playing with the surface plasmon energy, they can get either one type of exciton formed or another type of exciton formed, so you can basically choose. And they call this surface plasmon gating. And so you see here they either form this S2 state that then fluoresces, or they form an S1 state here that fluorescence, and they can cut off this one avenue. Now, why is that interesting? And this is because we're interested in driving these multi-exciton effects, and this effect here is what's called Singlet Fission, and in that sort of effect, what can happen, you have a molecular energy diagram in which you have a singlet state that is almost exactly twice the energy of a triplet state. Now what can happen in that case is that you excite the singlet state and it breaks up into the separate triplet states. So what happens now is that we have one photon absorbed and we create two excitons. And so this can double your quantum efficiency of your solar cell in principle. Now this molecule here, this Pentacene, doesn't do this by itself. And that is because the triplet is not precisely right. Now the idea here was that if we now hybridize that with a plasmon, we can tune that energy level just a little bit and actually drive this process to happen and drive it towards getting multiple of these triplet excitons out. So we put these Pentacene molecules on glass here first to get you familiar with this system. So this is ultrafast absorbance here. What you can see is, so this is transient absorbance. What you can see is that the singlet state is being created and there's a little bit of triplets being formed, which you always get. It's just a tiny little amount here. But nothing really special. This is actually well known already. Now you do the same thing, you put this on the silver nanohole arrays and the situation changes radically. You can still see that singlet being formed over here, but you can see a much larger amount of the triplets being formed. And that's this little peak over here. There's another state being formed here, which we have no idea what this is. But there's a lot of work to be done here, as you can imagine. And over here you can see another absorbance that is new that we cannot explain yet. But you can actually reproduce this effect, put spaces in between, so it's not just a direct contact with the silver that is causing this. So this is a silane on the silver, and you can still see the increased triplet being formed over here. So a little bit less, but it's still there. And when you use PDOT, it's also still there. So the effect survives that addition of the space layers. Now you can take these spectra, deconvolute it, and actually get to the different species as a function of time. So this here is just a bleach of the Pentacene, so that's the formation of the excited state, and then that lives for quite a long time, as you can see here. And then if we compare that with the formation of the triplet excitons when it's on glass, you can see this initial rapid increase and then a quick decrease and then a very long phosphorescence basically over here. When we put that on the silver nanohole arrays, and this is normalized so that you can see it, we can see that the yield increases by quite a bit, and for some reason that initial decay is gone. We also don't understand why that is, but we can say that there is a large increase in the yield of the triplets, and they have a large increase in their lifetime. Now we cannot explain this. The theory to really explain this is not known yet, so there's a lot of work to be done in this field. And with that, I'll just go to the end of my talk here and thank a lot of people that were involved. So I saw a lot of results actually that were done by Anthony Morfa, my ex-grad student. He's now in Melbourne. And Tom Riley, my postdoc. And there's a lot of other people that are sort of sideways involved with the research, and here are some papers for you to check out. And with that, I thank you for your attention.
Thanks for leaving plenty of time for questions. Does anyone have any? Yes, Kurt.
Oh yeah, I just curious. If we go to nanoparticle, like organic nanoparticle, then nanoparticle.
I'm sorry, organic nanoparticle?
Yeah, I was just saying that like you said the plasma effect. What happens with the organic nanoparticle?
So that happens with silver, gold, platinum. It happens with metals with a large density of d electrons, basically.
Okay. How about calcium and aluminum?
Sorry?
How about calcium and aluminum?
So aluminum has it too, but you normally never see it because of the aluminum quickly oxidizes on the surface, and you don't see it anymore. But aluminum in high vacuum actually has a surface plasmon.
So you want to anything to the organic nanoparticle?
No, so you need a lot of free electrons.
What do you think about using for enhancement of electric field a simple lightning rod effect instead of surface plasmons? For example, by sputtering iron and silver films on the surface. Yeah, use a lightning rod effect.
Yeah, it is certainly possible. Yeah, absolutely. That you just get better current injection into those ITO layers or whatever, that sort of thing. We don't see any evidence for that. If you do impedance on these systems, there's really no difference in the resistances of these interfaces and that sort of thing. So I don't think that's what's going on. And the optical calculations actually show that there is an enhancement just from solving Maxwell's equations in those systems. So I think it's fairly clear that that's actually an optical enhancement effect.
At the back?
Do you think the periodic CIMOPV is better than the random CIMOPV to get the plasmon effect?
I'm sorry, can you repeat the question?
Instead of right now your experiment is doing the random CIMOPV.
Oh, yeah, sure, yeah.
If you try the periodic, you will get a better plasmon effect.
You can get higher effects at very limited wavelengths. So if you make an ordered array, instead of a really broad peak, what you get is very narrow peaks at very certain wavelengths. And there you can get much higher effects, but only at very limited wavelengths. Also, they're much harder to make over large areas. I mean, we use the random array since they're really simple to make, actually. Plus, they have a really broad transmittance peak instead of this very narrow set of peaks that are basically, it's basically your refraction effect on the grating that you see when you have a regular array.
Yeah, so
Yeah, you.
just to clear up appropriately. So you have an excitement of field because of resonances in these nanoparticles, right?
Yeah.
And so these are size dependent then as well?
Yeah, they are in principle, although there's not a lot of change.
Oh, okay. So you don't get a different wavelength
It does shift a little bit, but it's not very strong. You get larger shifts if you go to different metals.
Oh, okay. So in general, people don't have to worry about using different sizes to create a broader spectrum.
You can, in principle, yeah. And when you look at those nanohole arrays, there you have a really large effect in the spacing. So if you bring them further apart, then the maximum occurs at a longer wavelength. That's different from the nanoparticles, which are much smaller, and there's very little effect on the size of the nanoparticle. It's there, but it's not very large. It's always somewhere in the blue, where you can see it in silver. It's somewhere in the red with gold.
Yes, actually my question is quite connected to the previous one. Did you think about the pattern of your surface by lithography, for example? Because in that case you can tune the surface for direct osmosis, because you know the nanoparticles distributed like uniformly on the surface.
Sure. Yeah, that would be a much cleaner experiment than these things, absolutely. But I don't have the access to this large scale. To make a solar cell, we really need at least 41 square centimeters or so, something like that. And typically these nano pattern things are much smaller than micron-sized type things. You can do it. So there are now places. So the nanoscience lab in Argonne can do this over very large areas, and There are other places where you can do this now, and they use these stamping methods basically, so you repeat the stamp a lot of times. It's all automated and all these sort of things. It's very expensive though, as you can see, and I like these much simpler methods of just evaporating oil and it just happens by itself.
So in that case, you would be sure that it was moving enhancement.
Yeah.
And here is quite difficult. It's more complex case.
It's more complex, absolutely.
How do you solve the problem of solubility when mix the nanoparticles into the active layer?
So that's very, very tough indeed. Yeah. You cannot get an awful lot in there. So right now it's just silver particles or octanomean groups on the surface, and you can get a little bit in, but not enough really to do a lot. On the other hand, I mean, with this already you can see you almost kill the cell already with just a little bit of the silver particles in there. We've taken cross-sectional SEM, and they really are throughout the layer. They don't bunch up on one side or something like that, so they really mix in. But to get really large enhancement effects, you want a lot more in there, but it just won't dissolve.
So they are mixed very well, or that you aggregate together.
So when you put too much in, it just doesn't dissolve at all. And in the end, you'll just get really rough layers with big chunks of silver particles lying around, and it will just short out the whole thing. So right now, it's just a few milligrams that's in there.
Maybe one last question.
So to have a rough array of silver nanoparticles, does depositing calcium fluoride or magnesium fluoride help to have a roughness on the top layer?
Oh, okay. I don't think that really changes very much, but you could make the top layer much rougher that way, indeed. I don't think it does very much. It's still a mirror if you have calcium
Yeah.
there.
Because I've seen somewhere they use a thin layer of salt, like magnesium fluoride, to increase
Oh,
the
okay,
roughness,
yeah.
which would
Yeah.
improve photon plasmon coupling.
Yeah, you can use light scattering there to get much better absorbance in your cells, absolutely. And you can do the same thing on the front. You can structure the ITO a little more. Other oxides are much more rough and give you much more light scattering at oblique angles. And, it's not really done in organic PV at the moment, but there's no reason why not actually.
Okay, so maybe we'll call an end to the formal questions then, and perhaps you'll join me back in the afternoon.